You're not going to believe this. I started a back test on Friday, for a new strategy I'm working on. It's Monday morning and it is still running. We're talking 3 full days. How in the world do the big shops get this done in like a few minutes? Well, they stop trying to talk at the computer and start speaking its native language. And that language, my friend, is parallelism.
Yes, that's the heart of it, right? It just feels completely hopeless. It's like I'm trying to dig a tunnel with a tiny spoon. There is absolutely no way this is going to scale up. And you're absolutely right. It doesn't scale that way. So, where do we start? With raw horsepower. We're talking about supercomputers. And look, these aren't just souped-up desktops. We're talking about machines purpose-built to crunch a mind-boggling number of calculations, what we call flops, or floating point operations per second. Usually, this means linking up thousands of processors into one giant high-performance computing or HPC cluster.
Right, so let's get into the why behind all this, because it's super important. Financial markets, they're not just complicated, they're what we call complex adaptive systems. It's a whole other level. Many of the problems we're trying to solve in machine learning for finance are what's known as NP-complete or even NP-hard. In simple terms, that means the problem's difficulty just explodes exponentially as you add more variables. Think about things like dynamic portfolio optimization or huge classification models like bagging and boosting. You just can't tackle these on a single computer and expect an answer this century. You really do need the heavy machinery.
Okay, but here's the thing. It's not just about getting a faster car. You also have to know how to drive it. You could have access to a massive supercomputer, but if your code is written inefficiently, you'll still be stuck in the slow lane. So the first and maybe the most important step is to write smarter code. And that all starts with a concept called vectorization. So take a look at this. This is huge. On the left, you've got these nested for loops. It's kind of the way a lot of us first learn to program, right? One thing at a time, step by step, but man, is it slow. On the right, though, we do something completely different. We replace all those loops with a single, vectorized operation. This specific example uses a cool Python library called itertools to do it. And the result? Well, it's not just cleaner code. It is way, way faster. Because deep down, the computer isn't running slow Python anymore. It's running highly optimized compiled C++ code. Whoa, hold on. So you're telling me just by changing how I write the code without even touching the hardware, I can get a massive speed boost? That's incredible.
Okay, my code is vectorized, I'm feeling good. But now, how do I squeeze every last drop of performance out of my machine? I've got this beefy server with 16 cores, but when I look at the system monitor, it feels like only one of them is actually doing any work. That is the perfect next question. The answer is multi-threading. It's time to tell your computer to stop thinking sequentially and start attacking the problem from 16 different directions all at the same time.
All right, let's make this real. Here's a classic problem. We want to simulate, say, 10,000 random stock price paths and find the very first time any of them touches a specific price barrier. This is something you do all the time in options pricing or for risk management. Now, here's the standard single-threaded Python code you might write to solve this.
Okay, running that code on our 16-core server, it takes 55.1 seconds. Burn that number into your brain. 55.1 seconds.
And this visual shows you exactly why it's so slow. Look at the CPU monitor. See that? One single core is screaming, pegged at 100%, trying to do everything by itself. Meanwhile, the other 15 cores are just chilling. They're totally idle. It's just a massive, criminal waste of potential. So here's the solution. It's beautifully simple, really. We rewrite the code to think in parallel. We take that big job of 10,000 paths and we chop it up into 16 smaller, bite-sized jobs. We hand one job to each of our 16 processor cores. Then we just say, go, and let them all run at the same time, reporting their answers back whenever they're done. That's what we mean by running asynchronously.
No way. Hold on. From 55 seconds down to 9.6? That's, almost a 6 times speed up? And I didn't buy any new hardware. This is just from using what I already had, but smarter. Okay. Mind blown.
Exactly. And here's the beautiful after picture. Now look at that CPU monitor. Every single core is lit up, firing on all cylinders, working together in perfect harmony. No more wasted potential. We've balanced the workload perfectly and finally unlocked the real power of this machine.
Okay, this is amazing for a single, powerful machine. I get it. But what's the next step? What if my backtest is just so monstrously huge that even one 16-core beast isn't enough? What if I need, like, a whole army of these things?
Then you've got to start thinking like a 4-star general. You need a strategy to organize your army, and in our world, that's called hierarchical parallelism. You break the entire war, your massive problem, down to manageable pieces. The smallest possible task, like fitting one single machine learning model. We'll call that an atom. Then, you group a bunch of atoms together that should run on the same machine. Maybe they need the same data set, and that's a molecule. Finally, the whole collection of all the molecules that solves your entire backtest, that's the group. And this kind of thinking is what lets you scale up to these absolutely massive clusters. Take a look at this. This is a real cluster at Berkeley Lab. What you're seeing here are 64 individual computers, or nodes, all networked together, bringing a grand total of 1,024 CPU cores to bear on a single problem. That's a digital army right there. So, how do you manage all that? You can't just yell charge. You need a command structure. We call it a master-slave architecture. One computer is designated as the master. That's your general. It doesn't do any of the actual fighting. Its job is to give orders. It hands out the molecules of work to all the other slave nodes. The slaves do the heavy lifting, report their results back, and the master puts it all together to get the final answer. And a good master has to be smart and resilient. If one of the slave machines goes down, the master has to be able to reassign its work on the fly so the whole mission doesn't fail. This is it's a whole new world. But it makes me wonder, are there problems in finance that are so ridiculously hard that even a giant army of classical computers would just choke on them? I'm thinking about things like multi-period portfolio optimization with real-world constraints, like you can only trade in blocks of 100 shares. The number of combinations just seems impossible to check.
You just walked right up to the edge of the next great frontier. For those truly impossible NP-hard problems, we have to look beyond classical computing to quantum. And here is the absolute best way to understand the difference. A classical computer calculates the laws of physics. It runs the numbers. A quantum computer, on the other hand, actually uses the bizarre laws of physics at the quantum level to do the calculation.
The magic here all comes down to the qubit. You know how a normal computer bit is either a 0 or a 1? Well, a quantum bit, a qubit, can be a 0 and a 1 at the exact same time, thanks to a weird property called superposition. And what that means is that the information capacity grows exponentially. As this quote says, an n-qubit system can hold 2 to the power of n units of classical information. This is why a quantum computer can explore a huge number of possible solutions all at once. And listen, this isn't just theory anymore. This is happening. Check out these experimental results from a D-wave quantum annealer. They tasked it with that exact kind of tough portfolio optimization problem we were just talking about. And for these smaller scale versions, look at this success rate. It was finding the optimal or very nearly optimal solution almost every time. It's a proof of concept for sure, but it shows that as these machines get bigger and better, problems we think are impossible today might just become trivial.
Wow, okay, my head is officially spinning, but in a really good way. So can't we just bring this all back down to earth? Can you just boil it all down for me? Like, what's the actual playbook? What should a quant be doing right now to take advantage of all this?
You got it. Here's your modern high-performance playbook. Number 1, vectorize first, always. Get rid of those explicit loops. It's the lowest hanging fruit and gives you huge gains. 2, go parallel. Use multi-threading to make every single core on your machine earn its keep. Don't leave free performance on the table. 3, for the really massive problems, you have to think hierarchically. Break it down into atoms, molecules, and groups. 4, schedule that work intelligently. Use a master-slave setup to command your army of computers and build in resilience. And finally, number 5, keep one eye firmly on the quantum space, because the problems that define the limits of today's finance might be the warm-up exercises for tomorrow's quantum computers.
At the end of the day, what this all comes down to is that speed is an edge. When you can compute faster, you can run more experiments, you can build more complex models, you can find the faint signals that everyone else misses. And that leads us to the final thought we want to leave you with. Your next big source of alpha is out there, just waiting to be found. The only question is, who's going to find it first? A classical supercomputer or a quantum one?